Welcome everyone. Today we'll be looking at flows through uniform pipes. The use of the Poiseuilles-Hagen's equation to solve for flows through uniform pipes, pipes of same cross-sectional area. Okay, so we have a question on the board that says an oil of viscosity 0.9 poise with relative density 0.9 flows through horizontal circular pipe. The diameter of pipe is 100 millimeter, pipe length is 10 millimeter. We have to determine the difference in pressure at the two ends of the pipe if this weight of oil is collected in the tank in this time. So pretty easy. We'll start solving this problem by bringing out the given parameters and converting them into SI units. So the first we have there is viscosity. Now you know we have two types of viscosity. We have kinematic viscosity and dynamic viscosity. So we know this is dynamic viscosity because its unit is in poise. Poiseuille. Its unit is in poise. So we convert. So this is how we convert. We know that (0.1 Newton second per meter square is equal to 1 poise. This equivalent in Newton second per meter square 0.1 is equal to 1 poise. And then if we have x will be equal to 0.9 poise. So we can do this simple math here. And then if we cross multiply, we'll have our x, which is our dynamic viscosity, giving us mu equal to 0.09 Newton second per meter square. Any difficulty there, we can confirm using our calculator to say 0.9 multiplied by 0.1, and there we go, 0.09 Newton second per meter square. So that's how we convert from poise to SI units. Great. So that's that. So let's write our value here. So that we can erase this. The second parameter I have is relative density. Now, we are not given the density of the fluid, but we are given the relative density. And you know, from our elementary physics, there is a relationship between density and relative density. Of course, we know our relative density, RUD, is equal to the density of fluid, in this case, oil, all over the density of what? Water. And then simply, if we want to get the density of fluid, we cross multiply. Of course, we know the density of water is what? 1000 kilogram per meter cube. So, our density of oil will be equal to our RUD multiplied by the density of what? Water. Right? So we have 0.9 multiplied by 1000 all in kilogram per meter cube. So this is 900 kilogram per meter cube. So we've converted, we've gotten the density of oil from the relative density of what? Oil. So we write it somewhere as rho of oil equal to 900 kilogram per meter cube. So we can erase. So we proceed. We know this is through horizontal circular pipe. So of course the pipe should look like this. The pipe is horizontal and then we know it's circular, so it has to look like this. So this is a horizontal circular pipe of same cross section. So the pipe has to look like this. So we're looking for P1 and then we're looking for the difference in pressure. The difference between the two ends of the pipe is what we are absolutely looking for. So this is the idea, this is the picture of what we are trying to solve. The difference in pressure as the fluid flows from this point at this point 1 to this point 2. So we want to check the pressure difference, because as fluid flows from one point to the other, there is always a drop in pressure at every point. So we want to check the difference in the pressure drop. Okay, so that's that. Then we have the diameter. We have the diameter as diameter D as 100 millimeter. So of course we know how to convert this from elementary mathematics. So this will be 100 what divided by what? 1000, right? Or 100 times 10 raised to the power of minus 3. And so this cancels out, right? This cancels out. So what are we left with? We're left with 0.1, right? So this is 0.1 meters. So we have our D diameter as what? 0.1 meters. So we can place. Then of course the pipe length L is already given in what? Meters. So it's 10. So there is no point to convert, because we're trying to bring all the units to uniform ground, where when we are solving we will arrive at a very accurate value. So what's left? The weight. Weight is in Newton. Of course, weight of what? Oil. The weight of oil is in Newton already, so let it be there. And then the time for which the oil was collected, time T, is equal to 20 seconds. Alright, now we have finished converting. It's time to solve. Now for this flow, remember, for flow through uniform pipes, you have to determine the nature of flow. If the flow is laminar or the flow is what? Turbulent. So if the flow is turbulent, you know there has to be a friction factor, because there has to be pressure drop, pressure losses, right, due to friction, because it's one of the major losses we encounter in the pipe flow. So we have to see if the nature of the flow is laminar or the nature of the flow is what? Turbulent, so that we apply the necessary conditions. So for us to know if this flow is laminar through this circular horizontal pipe or turbulent through this circular horizontal pipe, we use the Osborne-Reynolds number to determine. We use the Osborne-Reynolds number to determine. Of course, this is part of our non-dimensionless numbers. And so we use this number to determine. Now, how do we use this number? We know Osborne-Reynolds number given by RON is equal to density and the mean velocity multiplied by the diameter all over the dynamic viscosity, or the mean velocity multiplied by diameter all over the kinematic viscosity. So these two equations will produce the same value. Now, but we will use this, we will use this one because we have the density of oil as 900 already. We don't know the mean velocity, we know the diameter, and then we know our dynamic viscosity. So we will not look at this one because we have no kinematic viscosity. So of course this one has to go off. So let's work with this. Now remember, for us to get the value of Reynolds number, we need the value of the mean velocity, and we don't have the value of the mean velocity, so we would determine the value. How do we determine the value? Recall that discharge Q is equal to area A times velocity, mean velocity V, right? Also recall again that discharge is equal to volume all over time. And then again, this charge is equal to mass flow rate all over density. Of course, these three equations gives you a value for this charge for a particular amount of fluid flowing from one section to the other in a pipe. So, but in this case, we have two unknowns. So this equation basically will not work. We don't know this charge, we know only area, we don't know velocity, and we are looking for velocity in order to get our Reynolds number. So this is obsolete. For the second one, we don't know volume, but we know time, and we are looking for velocity, of course. For the third one, our mass flow rate can be determined from the weight of oil and the time, and the density is already known as 900 kg per meter cube. So we use the mass flow rate all over density. So I'm going to rewrite this and so that there will be space here. Our RON, Reynolds number is rho, mean velocity, diameter, all over dynamic viscosity, and then discharge will be mass flow rate all over density. So this is given as this all over rho of oil, right? Great. Now to determine mass flow rate, of course, we know from elementary physics that W is equal to mg, right? W is equal to mg, and we know the weight, so our mass m will be equal to weight all over acceleration due to gravity. So the weight is 700 all over acceleration due to gravity is 9.81. And so let's get the value of this so we know the value of the mass. So the value of the mass is 700 divided by 9.81 should give us 71.35. Right, so this absolutely should be in what? Kilogram. So that our mass flow rate, which is mass all over time, our mass flow rate, which is mass over time, will be given by 7.355 all over what? 20. T is 20. So we get 7.355 divided by 20. So we've got 0.36775. Now, well, to be the unit will be in kilogram per second. Remember, because the formula was mass over time, so mass is kilogram and time is second. So the unit will be what? Kilogram per what? Second. So that's the value for mass flow rate. So we'll impute the value here in order for us to get our discharge. Okay, so let me erase. So this is we started from the weight. You know, we can always relate weight, mass, and acceleration due to gravity for us to get our mass. We divided by time to get our mass flow rate. Okay, so let me write the value somewhere. Our mass flow rate is 0.36775 kilogram per watt second, so that I can write this up. Okay, so our discharge Q, our mass flow rate is 0.36775 kilogram per second. All over density of oil is 900 kilogram per meter cube, right? So kilogram takes care of kilogram, right? And then Q is equal to 0.36775 divided by 900. So our discharge is 0.000408 meter cube per second. How? Look at the units here. We had kilogram per second divided by kilogram per meter cube, right? So this will give us kilogram per second multiplied by meter cube per what? Kilogram. So that this goes, and then this is equal to meter cube per what? Second. So that was how we got meter cube per second as a unit of discharge, right? Alright, so now that we have this charge, we will now look for our mean velocity. Now that we have this charge, we will now look for our mean velocity. Let me put the value here. Q here is equal to 0.000408 meter cube per second. So now that we have our discharge, we can now look for our mean velocity. So we know that Q is equal to A times V, right? And then we'll also look for A, the area of the pipe. In the area of, since the pipe is circular, we know pi d square all over 4 will do. So this is 3.142 into the diameter is 0.1 all squared all over 4. So this should give us, simplifying further, we have this man. So we have 0.01 over 4. So further, if you multiply this by 3.142, so this gives us 0.007855 meters squared. Right? So that's our area. So A is that. So we can wipe it off and then solve. So this is our area of pipe. A is this. And then from this equation, if we make V our mean velocity subject, V will be equal to what? Q all over A. Right? So Q, we got our discharge. Q as 0.000408. Our area is 0.007855. And still keep the units. So for this charge, we have meter cube per what? Second. And then for area, we have meter square. Right? So our mean velocity will give us, let's divide out and see. So we have this 855. So what we are having here, we have 0.05194 meter per second. Of course, this goes here, and we have this. So you have meter per second. Pretty easy. So we have the value for velocity, our mean velocity here. So we equally bring it down here. And so we've gotten lots of values which will be of great importance to us as we proceed. So you've seen that we'll solve from the known to the unknown. As we keep going, a lot of things keep raveling. Okay, so this is this. You can always work yourself from here down. From our discharge, we made our mean velocity our subject formula, and then we had discharge over area. And we evaluated, so we got the value for mean velocity at 0.05194 meter per second. Okay. So the whole essence of going thus far is to get mean velocity, which we've gotten. So if we input the value of mean velocity in this equation, so we should be able to get our density of oil 900. Our mean velocity is 0.05 194. Our diameter is 0.1, and the value of our kinematic, our dynamic rather, not kinematic, dynamic viscosity is 0.09 Newton second per meter square. So of course, I like to work things pretty easy so you don't get confused. Now look, since Reynolds number is a dimensionless constant, look, let's check if the dimensions here will come out or not. If it does, we are wrong. If it does not, we are correct. So for density, we have kilogram per meter cube multiplied by, for mean velocity, we have meter per second. For diameter, we have meter. All over. For dynamic viscosity, we have, what do we have? We have Newton second, right? Per what? Meter square. Right? Of course, we know that this can cancel out. This can be written as kilogram all over meter cube multiplied by meter, right? Squared all over second all over Newton second per meter square. So this can go, this can also go. So of course we have Newton, we have kilogram per meter cube all over Newton. Now if we bring, remember, kilogram second per meter square. If you have F is equals to MA, right? This is kilogram. Acceleration is meter per second square, right? So if we have that, if we have kilogram meter per second square, then it means this whole thing cancels out, because you have second and you have second, and so you're having square. So everything strikes off to be what? Everything strikes off to be 1. So it is a dimensionless constant. It is a dimensionless constant. Everything cancels out. That is why Reynolds number does not have a unit. Alright, so that's just by the way. Then for our value of Reynolds number, so if we solve through, we have 900 multiplied by 0.00519 multiplied by 0.1, right? So we will have a value, say 4.6746 all over 0.09, and then if we divide by 0.09, we will now get 51.94. So let's check it out again just to be sure we are doing the right thing. So we have just to be sure we are doing the right thing. So 0.09. Okay. So we have this 51.94. So that's Reynolds number. So of course, you know, Reynolds number 51.94 is less than 2000. So of course this flow is laminar. Of course, you know, if this value of Reynolds number was greater than 2000, then the flow will be turbulent, but it is less than this, so the flow is what? Laminar. So since the flow is laminar, we will now apply the Poiseuilles-Hagen's equation. We will now apply the Poiseuilles-Hagen's equation. So we have a laminar flow. So let's go apply the Poiseuilles-Hagen equation to solving this problem, so to know the difference in pressure. So we write applying Poiseuilles-Hagen equation. We have, recall, we know that our head loss, right? Like explaining very well, your head loss, HL, is equal to what? 32 mu VL all over specific weight. So that's that, right? This is the head loss due to viscosity. That the 2 is just a number from the derivation. This is the dynamic viscosity. This is your mean velocity. This is the length of pipe, and then this is the specific weight of the fluid. This is the diameter. Okay, so, but we know also that head loss is this, the difference in pressure all over this, equal to 32 mu VL all over. Of course, this cancels out, right? So P1 minus P2 is equal to 32 mu V all over V square. So we will try to impute the values which we've gotten thus far, because this is what we are asked to look for, difference in pressure. But when we started, I drew the schematic diagram of the pipe and looked at the pressure at the first section and the pressure at the second section. So this is the difference in the pressure between both ends of the pipe. So we can always do this. This is 32 times our mu is 0.09 multiplied by our mean velocity, which is 0.05194. The length of pipe is 10 meters all over. This is 0.1 square. That is the diameter, and this is P1 minus P2. The difference in pressure between both ends of the pipe. So we'll work our way through this. Let's evaluate that. Let us evaluate that. So sorry, this is 32. So if we evaluate this, we'll have 32 multiplied by 0.09 multiplied by 0.05194, then multiplied by 10. So we'll have a figure. We'll have P1 minus P2 equal 1.495872. So we divide all through by the square of 0.1, which will give us 0.01. Yeah? Yeah? 0.01. So finally, our difference in pressure will give us 1.495872 divided by 0.01. And so we have 149.5872. So our P1 minus P2 will be equal to 149.5872. So pressure force over area, right? So this will be what? Newton per meter squared. So this is the value of the difference in pressure at the two ends of the pipe. So just pretty easy from the start to finish. Hope you enjoyed the video. You get more video from us as we proceed. Thank you so much. God bless you.